Presentation will be dedicated to the pre and post processor. You should have followed before the previous tutorial, which tells you how to download this interface from the web page. What you require to run the pre and post processor. So you need a computer equipped with Linux. You need a recent version of the measure called GMSH that you can download at the following address. You need MATLAB runtime v9.5, which is compatible with MATLAB 2018b. And you need to have the provided uncompressed archive with the executables and examples. So to launch an inversion, you should have a few files ready. So you should have first a custom-made file named instar.txt, which describes each interferogram. So each line corresponds to a different interferogram, and there are 8 different fields corresponding to the interferogram characteristics. The first characteristic is the interferogram short name. Then you have to know whether it's an ascending or descending path for the satellite. Then you have to know whether the radar was looking right or left. Then you want to know the track, then the wavelength, which can be C, X, or L, and then you need to have the radar Earth line of sight. So it's a unitary vector. Then you should have interferograms, which are binary files coded on 4 bytes. The extension should be .r4 or .nv. They should be corrected for orbital effect, but you can still have a constant shift because it's determined in the inversions. You should have an NV type header file, which is an ASCII file describing the location of the interferogram and the pixel spacing. Then you should have masks for the interferogram if required. These are binary files which have 0s for mask value and 1 for visible data. The masks have the same dimension as the interferograms. Then you should have a DEM because you want to use a realistic topography file. And so the DEM can be either binary files with a header included, or they can have a separate header, which is again an ASCII file. Let's now go to the X terminal, where you can see the downloaded archive. You can enter and unzip it with the command tar xvfz default.jz.tar. As it's already unzipped, I won't do it again. I will simply go to the directory created. It's called devvolc _ prepost _ compile. In this directory, you have a data directory with examples of data. You have an inversion directory with examples of inversions and the files that are created for each inversion. You have utils, which is a directory with different MATLAB utility files, and utils._compile, which is a MATLAB with a compiled version of these different files. Then you have a README file with the instruction for devvolc users and different executable. One to launch the pre and post processor, it's called launch devvolc. One to run the inversion, and one to run the appraisal. We will first read this file, and it tells you which instruction you have to type to launch the interface. So let's do that now. Now the interface is launched. So from here you can either open a new inversion or visualize a previous inversion. You can open a previous inversion, with a save file, or you can quit. Here we are going to start by opening a new inversion. You go in the inversion directory and you do go in test. So typically you create 6 different tabs. There is 1 tab per step in the inversion. The first step is the data preparation, so typically it's the interferogram undersampling or the downloading of the GNSS data. Then you have the source model definition, then you have the topography mesh creation, then you have the specification of the inversion parameters. In the 5th step you test the inversion, and then after running the inversion on the cluster, you can visualize your results. The eruption I'm going to model, to invert, is an eruption that took place at Piton-de-la-Fournaise in 2010. Here I will assume that I have 3 types of data, 2 interferograms and 1 GNSS data. So I say 3. When I validate, it generates 1 tab per data. So I will assume here the first data is an insert data. This menu here allows you to specify whether you have insert or GNSS data. And here below for this data you have 3 other tabs, 1 describing the data, 1 describing the subsampling parameters and the subsampling algorithm, and 1 describing the covariance matrix. I have to open the satellite geometry file, and this file is open once for the whole data process. Once the file is loaded, the menu appears here with the description of each type of data you can have. I will open the first data. I have 2 files, one with the TerraSAR X descending data and one with the TerraSAR X ascending. I will start with the descending data. So I need to specify here that it's a TerraSAR X descending data. Then I have created a mask file and I will upload it. So that's the mask here. Here, when I uploaded the interferogram, it read the header file with the number of columns, the number of lines, and the location of the interferogram. That's the location of the upper left corner, and that's the spacing along X and Y. Then I have to specify whether the insert data are radians or meters. I know that it is radians. And I have to specify whether the displacement data are displacement toward the satellite or whether it is Earth satellite distances. Mainly the difference between those 2 values is a sign. The sign is opposite. Let's assume it's the Earth satellite distance and check whether the subsample displacements are consistent with that. Next step is to accept and go to subsampling. So here I can have different types of subsampling algorithm. The subsampling algorithm can be circular, centered on a given value. It can be a usual quad-tree subsampling. The subsampling point may correspond to topography mesh nodes, or they can be regularly spaced horizontally and vertically. I will start by assuming that the subsampling algorithm is circular. I need to specify the center of the subsampling area. So by default it's at the center of the interferogram, but I want to have it at the maximum displacement. So I define another subsampling center by clicking on this button and clicking on the interferogram. Then I have to specify a subsampling interval. By default it's 150 meters. I will start with that, and a radius of finely subsampled area. Then I go to the definition of the covariance matrix. The default values are 150 meters and 5 square centimeters. These values were defined for Python La Fournaise. For this value, I'm going to show the data and the covariance matrix. What you can see here is that the maximum displacement here is moving toward the satellite, and it makes sense because this data here correspond to a fissure eruption located around here, and the uncoherent area here corresponds to the lava flow, and the incoherent area close to the lava flow. And here to the right you have the covariance matrix. I then move to the next dataset. Again, I will consider it's an INSAR data. I open the next TerraSAR X data, which is this time an ascending. I open a mask file. I need to specify the line of sight, so ascending, track 36. It's given in radians, and it's Earth satellite distances. I next go to the subsampling. This time I will try a quad tree. So quad tree basically is based on subsampling for high gradients or high displacements. So the higher the gradient, the more points you have. There are 4 parameters for quad tree. One is the minimum block dimensions in terms of number of pixels. The maximum block dimension, again as a function of the number of pixels. The displacement gradient threshold in a cell, and the displacement threshold in a cell. So basically quad tree starts by subdividing the image into large cells, and if the gradient is larger than the threshold, it subdivides the cell into 4 different cells, and it proceeds iteratively. I next go to the covariance matrix, again the same values as before, and then I show the data and covariance matrix. And if I like this undersampling, I go to the next dataset. The next dataset is a GNSS data. So I open the GNSS data file. The boundary of the file are automatically computed from the values given in the file, and then I accept it and go to the covariance matrix. So it shows here the GNSS data and the covariance matrix. And the last step is to make the concatenated data file from the 3 data files. The concatenated data file is shown here with the different subsampled displacement, and here you have the covariance matrix. The next step is to define the sources. So here I know that the displacements were created by an eruption, so I know that I have an eruptive dike, so that's my source. And then I may have a spherical reservoir, so I select it, I add it, and I validate it. In the upper part of the panel, you have the type of stress inversion that will be conducted by the inversion. So stresses can be either parameters, nonlinear parameters. So in this case, you have a stress change for the dike and a stress change for the reservoir, and these two are two linear parameters. So it adds two parameters to the inversion. To avoid that, another possibility is to define stresses as constant linear parameters, and for each combination of geometrical parameter, determine the best fitting stress change for each source. So you have different options. If all the data are consistent in time, you can assume that you have a single pressure change for all the sources. If your data cover different time periods, then you can have one pressure or stress change per data. So one pressure change, for instance, for one interferogram, and another one for another interferogram. If you have two sources and two interferograms, you will obtain four pressure or stress changes. Then you have to specify the Young modulus, the Poisson ratio, and here you can specify whether it's permitted or not to have fracture being interpenetrated. Because mathematically, fracture interpenetration is allowed, but physically it might not be desirable to have fracture interpenetration. So here you have one tab per source, and you can see that for each source you have a series of parameters. The different parameters are described to the right here by the scheme here. So for a dike connected to an eruptive fissure, the location of the fissure, for instance, is here, you need 8 geometrical parameters. So you need 6 geometrical parameters to describe the bottom part of the dike, 3 for the midpoint of the bottom part of the dike, and 3 for the length and orientation of the bottom line. And then you need 2 additional parameters, one which is an along deep curvature and another one which is an along bottom curvature. So that makes 8 parameters. These parameters can be fixed or they can be inverted. For instance, the deep, you can decide that you want to vary it between 60 degrees and 120 degrees. These degrees are indicated from the horizontal plane as indicated here on this drawing. And the same for the rest of the parameters. Again, for the sphere type of source, you have 3 parameters that define the center, the spherical source, and 1 parameter that defines the radius. So here I will define a topography mesh file, but as I told you, here we are looking for sources associated to an eruption. And because there is an eruption, there is an eruptive fissure, and the topography mesh needs to intersect this fissure. So the first step is to define the eruptive fissure. To do that, I have to open the interferogram. It loads the interferogram, 2 panels, and a schematic view of a typical fracture of an eruptive dike. So you can see that this fracture is made of 2 parts. One part connects the fissure to the ground, that's this fissure, and you have another part which defines the upper part of the quadrangle defining the eruptive fissure. So here, these 2 parts, the upper one and the quadrangle top, are defined on the left to the interferogram and on the right of the interferogram. So here I am first going to zoom on the interferogram. Then, to define the location of the eruptive fissure, I can either load a file that was maybe acquired from field data or acquired from another satellite image or any other way. But here I'm going to define it by hand from the interferogram itself. So I click on the left, user defined. And here I can specify the number of echelons that make up the eruptive fissure. Let's assume I have 2 echelons, and let's assume I want to reinterpolate this echelon with a step of 100 meters. I confirm that. So I have 1 tab per echelon. I will here start by considering the default number, that the first echelon is made by 5 points. So I select this button and I will start to select the points. So press here, and here I select the 5 points. Then I will move to the second echelon. This time I will assume it's made of 3 points, and I select the 3 points. Then I may want to reorder the points from south to north, and that's in order to have a reference for the deep. That's for positive deep, dipping eastward. So I reorder that. I can add point, I can delete points. So let's go to the first eruptive fissure, and here I can select the point I want to change, modify or delete. It's highlighted in green. So let's say I want to delete the first point here. I select it and then I click on remove point. If I'm happy with these echelons, I interpolate them and proceed. Then I have to define the quadrangle upper edge. So either I specify that it is the same as the surface fracture, either I load it as a file, or I defined it by hand as I did for the upper part of the quadrangle. Here I will click again on user defined. I will select 5 points. I reorder it from south to north, and then I save the upper edge. And once it's saved, I can go and prepare the mesh. The next step is to prepare the mesh from the eruptive fissure. So here the previous interferogram is automatically loaded, and my next step will be to define the center of the mesh. So usually it makes sense to have a fine mesh where the displacement gradients are high. So it makes sense to have the center of the mesh located where the displacements are the highest. I will do that by selecting this button, select Other Mesh Center. The default values for the radius fine mesh and the radius coarse mesh are very large compared to the dimension of the inflated area on the interferograms. Here you can see a scale in kilometers, and you can see that the area of large displacement has an approximate radius of 2 kilometers. So here I will modify this default value and have 2,500 meters as the radius fine mesh, and for the radius coarse mesh I will take 8 kilometers. Then I will open a digital elevation model. And then I will create the topography mesh. Here I can see that the number of mesh nodes is 3,800, and a rule of thumb is that this number should be this value, but the smaller the better in terms of inversion speed, but the smaller the less accurate. So you need to find the best compromise between the number of mesh nodes and the inversion duration. So here you can test the quality of a mesh using this function, meshtest.m, which is also available in a compiled version. So here, as the number of mesh nodes is a little bit large, I'm going to diminish the radius fine mesh, and I will diminish it to 2,200, and again recreate the topography mesh. Okay, now I have 3,200 mesh nodes, which is reasonable for an inversion. The next step is to define the inversion parameters. So you can click here or here. So you have different sections here. This section characterizes the number of forward model in the first iteration, and this one the number of forward model in the subsequent iteration, and this characterizes the stop criteria. For the first iteration, it depends on the number of model parameters, and it corresponds to the number of natural neighbors as defined by Sandbridge. The number of forward model at the subsequent iterations was determined by Fukushima and others. You can find the references for these two papers in the short course that comes along with this interface. Then for the stop criteria, you have two criteria. One concerns the standard deviation on the estimated models. It's estimated here on the 50 last models, and the standard deviation has to be less than 0.3, and the other criteria is the maximum number of iteration. This number is also determined empirically, and it also depends on the number of parameters. And here, the last section is the number of simultaneous computation, and it's given as 50 because it's the number of cores you have on the University of Clermont-Auvergne cluster. So the next step, the final step, is to test an inversion and evaluate the runtime. So I go to inversion and launch. So here is a summary of the different inversion parameters, and here of the different files that were generated. Two fracture files, one for the eruptive fissure, one for the quadrangle upper side, a topography mesh file, a data file, and a covariance matrix file. If I click here, I generate an input file for the inversion called param input. And if I click here, I can test a mean model and evaluate the runtime it takes. So I know the mean test is completed because a series of plots appear on the screen. These plots are a description of the mesh. Another is the openings on the different structures, the spherical reservoir and the dike. Another one is the shear displacement corresponding to the mean model, the mean value of the different parameter range. and another plot is the displacements vectors. Then I have a plot with the data, model, and residuals for the first interferogram. And I have another plot for the second interferogram. And then I have a plot for the GNSS data. So the data, model, residuals again. And if I want to see the runtime, the estimated runtime, I have to go to the X terminal from which the inversion was started. So that's this window. I can see here that the estimated inversion duration is very large, so it's 636 hours. I can also see the estimated overpressure, the data shift. I can see the average opening, the volume change, and the same for the dike, for the sphere, and the percentage of explained data corresponding to this mean model. Here I have a very large duration for the inversion, so it probably comes from the fact that I have a large number of parameters. So what I would suggest doing is to go back to the inversion and diminish the number of inverted parameters. For instance, I can start with a simpler model, assuming that the twist is fixed to 0. I can assume that I have no bottom curvature, for instance, and that the vertical curvature is also fixed, and maybe I can fix the radius of the sphere. It's very cool reservoir. And then I can go back to a mesh and rerun the computation, and a reasonable inversion duration should be a few days. When you have finished, you need to save, because you will need the save file to retrieve a previous inversion, and you will also need the save file for the result visualization. Specifically, you will need it to compare the data and the model. So you press save. You indicate the save file by giving the directory. Automatically the name corresponds to the date and the time. So you press the save file and the project is saved. So then I go to the web interface. I launch the inversion as I explained to you in the first video, and the next step is to visualize the result. So here I'm going to show you how to visualize results of an inversion. So I go to the result visualization, and I can, for instance, visualize the convergence. So I open the convergence visualization tool, and I open one of the files generated during the inversion. So one is called result.nares. That's where the results of the inversion are. I open this file. I select the param input file corresponding to the inversion. The inversion also generated a press shift.txt file that I open here. And then I press visualize convergence to visualize the convergence. Several files are generated. One showing the misfit for the parameters versus parameters. So the lower the misfit, the green correspond to green colors, higher misfit to blue, and larger to black. Another plot is this one, which plots the cost as a function of the parameter values. The smallest values correspond to the cross. Another plot is the parameter value versus the number of iterations. Then you have the cost versus the number of iteration. And that's it. And you can have a look at the X term from which the interface was launched. And here you have the bound of the search and the best fit parameters. You can now investigate the appraisal. So you click here to open the appraisal visualization tool. So you need to select the parameter file. You need to select the file resampled during the appraisal. To know more about this resampling method, you can have a look at Sandbridge paper or Fukushima and other paper. You need to open the result file and the pressure file. I recall that I inverted for 10 parameters, and then I can visualize the appraisal. A plot is created. On the diagonal, you have the marginal 1D probability density function, and off the diagonal, you have the marginal probability density functions in 2D. The red color indicates the mean model, and the blue color indicates the maximum probability model. If I look at the X term from which the inversion was launched, I can see here that I have the mean model and its standard deviation, the best fit model, and here is the minimum confidence bound, the maximum confidence bound for the 95% confidence. The length of the confidence interval, it's parameter per parameter. The first parameter is the dip, the second the shear, and so on. The next step is to visualize the volume, opening, and meshes. I click here. I select just the inversion directory. And if I want to compute the opening at the surface, I select a mesh file. Then I can visualize the opening in perspective or in 3 views along different directions. So let's start with the perspective, and that's the pan factor. So different plots are created. Again, one with the openings, one with the shear displacements, and one with the displacement vectors. And if I have a look at the X term, it gives me the dike opening, because here the inversion I'm showing you is only for one single dike. Now if I want to have more finalized files, I can select a DM rather than a mesh. So I go to the data section here, and I select a DM, and I can plot 3 views. This time I get displacement vectors, I get shear displacements, and I get openings. And finally, I can visualize the data model comparison. So I click on the data model comparison tool. I open the save file. And it loads the DEM, the topography mesh, the fracture file. Then I select the result file. So the best mode underscore res corresponding to the best fit model. I open that file. And then I can show the data model comparison by pressing this button. And I obtain the data model comparison. So first the data, then the model, then the residuals. And I can see these data wrapped or unwrapped. If I go to the X term, it gives me again the dike opening, the shift for the data, the percentage of explained data, and the RMS on all data, the mean residual, and the total percentage of explained data.